Welcome to Scale Up University. Welcome to the course on designing data intensive applications. So, this is the lecture 3 of module 1. And in this lecture, we will be discussing why trade offs are inevitable. So, if we look at the lecture overview, like what exactly we will be looking at in this lecture, now there is a blunt truth about the architecture, and that truth is if someone claims their system is fast, cheap, scalable, consistent, and simple. Either they are lying or they are measuring nothing. So, the moral of the story is that we cannot have a system which can be fast, cheap, scalable, consistent, and simple all together. There is always a trade off. Like if it is fast, then it cannot be cheap. If it is scalable, then it cannot be simple. Some complexities will be associated with it. So we cannot have a system which can be fast, cheap, scalable, consistent, and simple at the same time. So that's a like a very harsh or a blunt truth about the architecture or the computing system, and hence we are calling it like a impossible dream. Like it's an impossible dream to have a system which is fast, cheap, scalable, consistent, and simple at the same time. Because if we talk about the real systems, there is always a trade-off. Like improving one dimension always degrades another. So we can say that architecture in the real system, architecture is not about perfection. Rather, architecture is about choosing what to sacrifice. Because trade-offs will always be there, and we have to sacrifice one thing or the other. Like if we want speed, then we have to like bear some additional cost for that. If we want simplicity, then we have to sacrifice scalability. So the idea is we should stop searching for the best system and start asking best for what, under which constraints. So it's a very important discussion we will be making in this lecture, because any system design you will be making, you will be dealing with a building a architecture, software architecture. So trade-off is something which is inevitable, and that is what we will be looking in some good detail in this lecture. So in the after like at the end of this lecture, you will get a realization why trade-offs are inevitable when designing some real computing systems. So if we look at the topics that we will be covering in this lecture, so we'll discuss the root cause, scarcity of resources. So the main reason for the trade-offs is the scarcity of resources. Then we'll discuss conflicting goals in system design, why perfect systems don't exist, engineering as decision making under constraints, the eternal tension, cost, scale, latency, correctness, real world intuition, trade offs in practice. So, all this we will cover, like all these topics we will cover in this lecture itself one by one. So, this is the module 1, trade offs in data systems architecture, lecture 3, why trade offs are inevitable. And we are starting with the first topic, the root cause, scarcity of resources. So all trade-offs ultimately exist because resources are finite. Because of the finite resources, because of the limited resources, there exist trade-offs. Because time is also a resource, cost is also a resource, money is also a resource, and computing power is also a resource. So, and all these resources are limited. Time is limited. The budget, the money is also limited. Everything is resource finite. So, because of the finite resources, trade-offs exist. Now, if we look into some resources, so CPU, CPU is like the computing computational power. So, computation is not free. So, there is a constraint associated with CPU. So, CPU constraints, if we talk about, we have limited instructions per second. because there is a limitation on the number of instructions we can execute per second. Context switching overhead, because context switching, it takes some time. There is a lag associated with it, and it's a constraint. Contention between processes. Now, let us suppose you have a dual core architecture wherein two processors are working simultaneously. Still, there is a, like, processors are competing to get processed, to get the CPU, to get the processor. So there is always a contention between the processors. So hence, CPU constraints are always there. Limited instructions per second, context switching overhead, contention between processors. Now, if we talk about the trade-offs involving CPU, so CPU load. Okay, so see, if we talk about the trade-off, so the first trade-off we can discuss is the disk space. Like if we try to optimize the disk space, then what we have to do, we have to compress the data. So compression, it will definitely save the disk space, but it will cost CPU because we will be needing to run some additional compression algorithms. That compression algorithms, it will definitely reduce the disk space utilization, but it will also incur some additional cost. If we try to optimize the security, so security, we can consider encryption. Encryption will definitely improve security, but it adds latency. And if we try to optimize application logic, and for optimizing application logic, we can consider complex queries. But complex queries, it will definitely reduce the application logic, but increases the CPU load. So ultimately, if we try to optimize either the disk space, security, or application logic, ultimately we are increasing the CPU load. And because of that, there will be a latency and CPU will be occupied. So performance will get affected. So that's the trade-off. If we try to optimize one thing, we have to sacrifice the other dimension. So that's the trade-off. Now, one very interesting thing about CPU is that it is elastic in nature. Elastic in nature that we can scale it. Either we can do horizontal scaling or we can do vertical scaling. Where in horizontal scaling we can keep on adding more replicas of CPUs, and in vertical scaling we can improve or increase the computing power of the existing CPU by adding more processors into it. If it is dual core, we can make it quad core or octa core, wherein 8 processors are running simultaneously. Or we can do the horizontal scaling. So CPU is elastic, and that's a good thing. But still, it is elastic, that's totally fine, but still, it is never infinite. It is finite. It has to be finite. It cannot be infinite. And that's a limitation. And because of that, trade-off exists. If we talk about the second resource, that is memory. Now see here, when I talk about memory, I'm talking about the primary memory, that is the RAM. So if we talk about the characteristics of memory, so it is extremely fast. It is extremely fast. It is limited. This is a very big constraint. It is volatile in nature, wherein once the power is off, the data, it's gone. Data is not stored permanently in memory, and it is very expensive per byte, and hence it is limited because it is very expensive, and we cannot use like unlimited memory. It will cost money. Now, if we talk about the trade-offs associated with memory, now if we go for caching, what happens is that any repetitive data we want to access, instead of calling it from memory again and again, we can store it in an intermediary place called as cache, which is extremely fast as compared to memory. So with caching, definitely latency improvement we can get, because our data, we want to access it frequently, we can just access it via cache. So caching, definitely it improves the latency, but risk is also associated, and there's a staleness risk. The data might become stale, and what it means is that, see, The source of truth is in the memory, the original record, and in the cache, it's a replica of it. Now, what if the original records get updated? Because processor is now taking that data from the cache and not the RAM. And if that data gets altered in the RAM, so processor will be making use of a old data. So stale means here old data. Because the original data it got updated, but in the cache still the old data is there. So that risk is the staleness risk. So trade-off is there. Like if we over rely on caching, then staleness risk will amplify. If we go for in-memory database, so in-memory databases, it will definitely speed up. It will speed boost, but it will also at the same time increase cost because we know that memory is expensive. Large memory footprints, it will reduce concurrency. So the idea is that if we try to optimize one dimension, we have to sacrifice the other dimension. So that's the trade-off we are talking about. And hence, all the decisions we will be taking as system in system engineering or system design, it has to be highly contextual because the decision will depend on the problem which we are trying to solve or the goal we are trying to accomplish. There is no one hard and fast rule which we can apply in all the scenarios. For every scenario, the decision will be different because of the trade off. Now, let us look at one very important insight. See, memory optimizes speed at the cost of durability and money. So, definitely, we make use of memory. Why we use memory? Because we know that hard disk it has got a significant lag. Like if you are accessing the data frequently from the hard disk, it has a significant lag, so the performance will decrease. It will degrade. So for high performance, for low latency, we have to make use of memory. So memory definitely it reduces the lag, it optimizes the speed, the performance. But with memory, we have cost. We have to bear the cost and also the durability. And why durability? Because memory is volatile. The data in the memory, we cannot rely on that. It will fade away once the power is gone. So memory optimizes speed at the cost of durability and money. So it is fast but fragile and pricey. Disk. So here when I talk about disk, I'm talking about the hard disk, which is like the permanent storage. Now disk, they are durable but slow. So if we talk about the properties of the disk, so the one of the very important property of the disk is it is persistent, wherein the data is stored permanently, even power loss, the data will still be there. It is cheap as compared to memory, low cost storage, and it is slow, by very high latency. It's like a very big drawback of disk that it is very slow as compared to memory. High latency is associated. If we talk about the trade-offs associated with the disk, so see, writing to disk definitely it improves durability because the data is stored permanently. If you write the data on the disk instead of memory, then durability will increase, but also latency will increase because the read write operation, IO operation on disk is like it has got lag, latency is associated with it. So that is a trade off. Now, if we talk about replication, so if we replicate, if we make multiple copies of the data, then definitely it will improve fault tolerance. It will improve fault tolerance, no doubt in that. But it will also increase the write cost because now we have to write on different locations because we are maintaining a copy, a backup. So that's the trade-off. So if we want to improve the fault tolerance, then we have to bear some cost. It will increase the write cost. And if we go for indexes, so with indexing, definitely we will get speed reads, but it will also result in slow writes and it will consume more disk. So that's the trade-off. So if we try to improve one dimension, we have to sacrifice the other dimension. That's the trade-off associated with the disk. So if we talk about the disk trade-off pattern, so while using disk, you pay for durability with time. Like you are preferring durability over time, because using disk means persistent storage. But at the same time, you are also affording or incurring more time. It takes more time for the read and write operation. So here the trade-off is that we are going for durability safety by sacrificing the latency and the cost, time and cost. So that's the idea. Now, if we talk about network, so network is the silent bottleneck. Now, network is basically the communication network, like the systems they are connected in a network and they can exchange the data. Now, in network, so latency dominates distributed system. So in distributed system, multiple nodes are connected with each other, and that transfer or the information exchange, it takes some time. So latency is like a very big problem in distributed systems. Also, in distribute in networking, packets gets dropped. So it's a reality of a network. So latency, packet drop, message may arrive late, message may be duplicated, or message may be out of order. So these are like some very harsh realities of network. So network failures, it look like slow machines. So it's also a very harsh reality wherein we keep on waiting without realizing that some network failure is there, some fault is there in the network, and we feel that network is slow. That's why the message haven't like it hasn't arrived till yet. So we keep on waiting for the message to arrive without realizing the network failure. So network failures, it always look like slow machines. So these are like some very harsh realities of network which we have to deal, like latency, dropping of packets, messages arriving late, out of order, duplicated. So network failures, it look like slow machines. Now, what are the trade-offs if we talk about? So distributed systems, they scale better but fail harder. So uh, this is a very important discussion we are making. So in distributed systems, the scalability is the thing which we are trying to achieve, because in distributed systems we keep on adding more and more nodes and we are scaling it up. So distributed systems, we are trying to optimize the scale, we are trying to scale up the system, but the thing which we are sacrificing is the simplicity, because distributed system, it is becoming more and more complex, and hence handling uh, failure is very tough, because when the distributed system fails, it fails harder, and that is what we are sacrificing. So that's a trade-off. Now in a network, replication improves availability but hurts consistency. So when we maintain multiple replicas of the same node, definitely it improves availability. Like once the like one node is down, we can call the backup node. But also maintaining consistency is very tough, because any update, you have to update it on all the replicas at the same time. So that's a challenge. Cross region systems improve resilience but increase latency. So latency we already saw that. So the idea is that if we try to like make a network covering different geographical regions, that will definitely improve the resilience, but also because of the scale of the network, uh, geography, different geographies, the latency will come into the picture. Latency will start dominating. So it's a trade-off. If we are trying to optimize one dimension, ultimately we are sacrificing and suffering the other dimension. So one very harsh reality about the network is the network is unreliable by design. So we cannot rely on the network, and hence we have to assume, or we have to like make a mind mind makeup that okay, network will fail, and hence we have to work with the mindset how to handle that failure, because network is highly unreliable by design, and we have to keep in mind that network failure is common, and the most important question in front of us is how we will handle the failure. That's the idea. Conflicting goals in system design. Now most architectural goals, they directly conflict with each other. Let us look at some examples of it. If the goal is low latency, like we want less lag and high performance. Now low latency, it conflicts with strong consistency, because when we want ultra fast systems, then maintaining consistency will be a challenge, because to maintain consistency there is a need for coordination, and it costs time. Coordination needs some time, and if we are focusing on coordination, we are losing the ultra high performance. So if we want ultra high performance, very fast, low latency, then we we are conflicting with the strong consistency. So the trade-off we are talking about, or the conflicting goals we are talking about. If our goal is high availability, then it is conflicting with strict correctness. See, the idea is that system availability versus system correctness, both are different. Availability means regardless of showing up the most recent record, system has to be available. It's okay for a system to show a slightly old record. That is affordable when I talk about availability. But when I talk about strict correctness, then if the system is taking a delay in generating response, it's totally fine. It's totally fine for the system to like like uh, we can wait for the system's response, but we want correct answer. We want the most recent data, the current data, the live data. And strict correctness is something which is like mandatory when we talk about banking systems, fintech banking systems. Here availability is not that important, strict correctness is more important. So we cannot have both. So if we are aiming for high availability, so in e-commerce, high availability is more important. Wherein if the data is slightly old, it's totally fine. But availability is something which is more important over correctness. But in banking system, strict correctness is more important over high availability. So here, failures force choices. Now, if we talk about if our goal is scalability, then it is conflicting with the simplicity. This we already saw, because when we scale the system, the distribution, it adds complexity. If I talk about durability, it conflicts with performance. Durability conflicts with performance, because durability means trust, safety. That is durability, like the persistence. But there will be certain lag in order to ensure durability. Some lag will be there. So performance, it will conflict with the performance, because persistence is low. Persistence is low. So performance issue will be there. If I talk about cost efficiency, so my goal is cost efficiency, then it will conflict with redundancy, because in order to create replica, I have to like invest in so safety cost money. So now with this discussion, it's like we got a very important realization that one cannot be perfectly correct under all failures. So you cannot be perfectly correct under all failures at all scales with minimal cost and minimal latency. So the idea is that we cannot be perfectly correct, like we cannot handle all the failures, we cannot scale to like a very large extent, we cannot have optimize the cost and make it minimal, and minimal latency. So we cannot have all this at the same time. So something must give, we have to sacrifice something over the other. So this is what we started this lecture with. So the idea is very clear now. Like in system design, trade-off is always there. Trade-off is like a, it's like a harsh reality, and we have to keep that in mind. So if we are trying to optimize one dimension, then we have to sacrifice the other dimension. Why perfect systems don't exist? So the perfect architecture is a myth. Perfect architecture is a myth. Now, see, beginners, they ask a common question, like if somebody is new in system design, they will ask questions like which database is best, without realizing that nothing is best. It depends on the context. Which system solves all problems? So these are like some questions which beginners ask. Which architecture is future proof? Now the answer to all this is none of them. Like we don't have any best database. We don't have any system which can solve all problems. We don't have any architecture which is future proof. So the idea is perfection is impossible. And why perfection is impossible? Because workload changes, scale changes, business priorities change, hardware fails, humans make mistakes, because we live in a very uncertain world where change is inevitable. Workload changes. So with changing workload, there is a need to consider resources. When scale will change, there is a need to re-strategize. When business priorities change, there is a need to adapt. So one very important observation: any system which is optimized for today, it becomes suboptimal tomorrow. It's like a reality. So if we look into the data, like designing data intensive application insight, architecture is a snapshot of assumptions frozen in time. So this is a very interesting insight I'm sharing with you. So the architecture is just a snapshot of assumptions frozen in time. So whatever assumptions we are making now, architecture is a snapshot of that, and it is not like this assumption will work forever. After a while, with changing world, with the changing conditions, we have to change the architecture. Because and one very important observation, since architecture is a snapshot of assumptions, when assumptions fail or when assumptions change, trade-offs break. So the architecture, it will start breaking, and there is a need to evolve or to maintain it, to re-strategize. Engineering as decision making under constraints. Now see what engineering actually is. Let us first get a feel of it. So see, engineering is not writing clever code. No, that is not engineering. Choosing trendy tools is also not engineering. Engineering is not about writing good code or choosing trendy tools. Engineering is about decision making, making irreversible decisions with incomplete information, like making irreversible decisions, making decisions with incomplete information, making decisions under resource constraints while accepting risk. So that is engineering. So engineering is all about making right decisions, irreversible decisions in an uncertain world where information is incomplete and where resource constraints are there, and hence risk is also associated. So if we look about the key constraints which engineers face, so budget is like a very big constraint. Team size, time to market, regulatory requirement is a very big constraint, and operational expertise. So every architectural choice encodes a bet about the future. So good engineers, what they do, they make trade-offs explicit. They document assumptions. They understand consequences, and they design escape hatches. And it is very important. So now, see this. The slide which we are discussing, it's very important because system design is more about the mindset. It's not about coding. It's not about choosing trendy tools. That anybody can choose. So in order to be a true engineer, if you want to do very good in system design architecture, You have to make irreversible decisions with uncertainty in place, under resource constraints, and what constraints you will be having is budget, team size, time to market, regulatory requirements, operational expertise. So you have to make decisions, and in while making decisions you have to keep trade-offs in mind. Uh, Based on the scenario you have to decide which dimension to optimize, sacrificing the other dimension. Trade-off, you have to document as assumptions, because every architectural choice is a outcome of a assumption. You have to understand the consequences and design escape hatches. The eternal tension: cost, scale, latency, correctness. So we already saw the constraints. So these four forces dominate all data system design. So whenever you're designing a high intensive data system, you have to consider these four factor. First one is the cost. And when I talk about cost, I'm talking about hardware cost, because hardware will be involved, cloud services will be involved, operations cost, and engineering time. Reducing cost often means less redundancy, because less redundancy will be lead to less cost. Reducing cost often means high risk, because if you don't maintain proper replica, then high risk is there. Reducing cost also means slower systems. Then we have scale. So when I talk about scale, so we are scaling users, we are scaling data volume, and we are scaling geographic reach. Now, scale introduces distribution, coordination problems, and operational complexity. Then the next very important factor which will dominate the data system design is the latency, user experience, SLAs, real time expectations. See, latency, what it will lead to is user experience, because if we design high performance systems, then user experience will enhance. Service level agreements, real time expectations we will be able to fulfill. Low latency often requires caching, replication, and approximation. Then the fourth factor is the correctness, very important. So in data system design, correctness plays a very important role, wherein we want correct data. So it ensures data accuracy, consistency, ordering, durability. Durability means safety. The data is permanently stored. So correctness cost time. So to achieve correctness, there is a lag is there, because we are storing it in disk. So right operation will be expensive. It will take more time. Coordination. Correctness means coordination and complexity. So now it's very clear that whenever we are designing a data system, we have to keep in mind, we have to consider the cost, the scale, the latency, and the correctness. Now the problem is that we can never optimize all the four. We can usually optimize any two. Like if you are optimizing the cost, then you are sacrificing the latency. So you can optimize the cost and scale to certain extent. So you can optimize two or sometimes three, but you cannot optimize all four, and hence trade-off will be involved, because when you're trying to minimize the cost, ultimately you are sacrificing latency and correctness also to some extent. Scale also you are trying to, but if you are willing to pay more, but if you are trying to sacrifice correctness, like it depends, like the trade-off. So the idea is very clear that trade-off will always be there. Like we cannot optimize all four, and hence in system design we have to be very much careful in making the right decision, and that decision cannot be generic. It is highly contextual. It depends on the scenario, the problem or the goal you want to accomplish. Now let us look at real world intuition, trade-offs in practice. Now see, if we talk about banks, For banks, correctness is more important than latency. For social media, availability is more important than consistency. For e-commerce, availability is more important than strict consistency. And for ML systems, scalability is more important than strict correctness. In ML systems, if like we don't want strict correctness, but we want scalability. So the moral of the story is that, like, after looking at some real world scenarios, no system is wrong. It is contextual. Like here, all the systems are working properly. Like in ML systems, we are sacrificing correctness. Still, it is working. It is not wrong. In social media, we are sacrificing consistency over availability. It is totally right. So, which dimension to choose? It depends on the context. Because in bank, if we go for availability over correctness, then it can be a disaster. Because in bank, correctness is the most important deciding factor. So correctness is more important over latency and availability. So finally, we completed this lecture. So in this lecture, we saw trade-offs. They exist. They are inevitable because resources are finite. Conflicting goals are unavoidable. Perfect systems are a myth. Architecture is about choosing pain because we have to make hard decisions. Good engineers, they understand what they are sacrificing. So it's all about the mindset. So I hope you got a very good understanding of the concepts which we covered in this lecture. So do subscribe to our YouTube channel, Scale Up University, for more such interesting lectures and courses. Thanks for watching. Thanks for your time.